Hey everyone, this is the second video for section 3.1 in advanced math. So we left off right here at natural base E. So remember, E is just a number. It's equal to that, and it comes up often in financial applications, so that's why it was assigned a special name, if you want to call it that, E. It's called the natural base. It is a function. The graph of it looks like this. Again, it has that same y-intercept. It's called the natural exponential function, and the inverse, this might come up later, but I'll just put it in here right now. The inverse of e to the x is the natural log of x. So on your calculator, you will notice that e to the x and natural log share the same button. That's because they are inverses, just like x squared and the square root of x. So this is just, again, oops, sorry about that, practicing putting some values into your calculator. So you're going to use that second natural log button for e to the x. If you have an 84, it hops it right up there and shows you that it's an exponent. So if I put in -2, I'm going to get that decimal. So practice putting these in your calculator. You will need to be able to do that for your homework and your tests and quizzes. So again, pause the video, check what happens when x is -2 and when x is 0.25. Make sure you're getting those decimal equivalents. So now where e to the x comes up the most, or e, I guess I should say, is when you're looking at interest problems where your money is in the bank and it's gaining interest and where it's compounded continuously. So that is where we're going to use E often. I'm going to go right to, so the book goes through a lot of examples where they're actually deriving our formulas, but I'm going to go right to this. So this is also in your book, but this should go in your notes. So these are formulas for calculating interest. So there's two formulas depending on the type of problem that you have. So in both of these formulas, T is your years. A is the balance in your account if you want to think at the end. So that's your final amount after you've earned your interest. P, it's called P because it's called the principal. That's a financial term for your initial amount. So this is how much money you put in the bank to start. The interest rate is R. Notice this says in decimal form. So if you're given, I don't know, 3%, think per century, we want to divide that by 100, and we have to plug in the decimal equivalent into our formula. And N, where do they have it up here? N is the number of compounding periods. I have it right here. So if they say you're compounding quarterly or biannually or monthly, then you're going to have an N value. If they say you have continuous compounding, you're going to use this formula. So you're going to need both of these formulas in your notes, and then this sort of tells you what each of those variables stand for, or letters stand for. So definitely pause the video, make sure all this is in your notes. Now, example 8, we are going to look at a problem. So in this example, we're putting $9,000 in the bank, or investing $9,000 at an annual interest rate of 2.5%, compounded annually. So that means once a year. And then it says find the balance after 5 years. So my initial amount is $9,000. My interest rate is 2.5, but remember we want to divide that by 100, which would be 0.025. My time, or my T, is 5 years. I am compounding annually, so that means n is 1. So I am using this formula. Principal 1 plus r over n to the n times t. So I'm solving for A. Find the balance in the account after 5 years. So that's my final amount. So it's going to equal my initial amount. 1 and plus is a copy job. R is 0.025. N is 1 to the 1 times t. T is 5. So this is just going to be 5, and this is just going to be 0.025. But you can, if you use your parentheses properly, let me clear this, you can put this whole thing in your calculator. See how well this shows up. So I'm going to put in 9,000, parenthesis, 1 plus. I'm going to put in the 0.025 divided by 1, but because it's a fraction, I'm going to wrap it up in parentheses, and you should do the same. Now, I know divided by 1 is just going to be 0.025, but I wanted to show you to put that fraction in parentheses, and then another parenthesis, and then this is going to be to the, I put my exponent in parentheses also, n, which is 1, times t, which is 5. And so then you're going to get an answer, and make sure it makes sense. If I invested $9,000 and after 5 years I have 10,000, that makes sense. If you get a number that's less than 9,000, you probably punched something in wrong. So what I got here was 10,182.67392. So this is approximately $10,182.67. Okay, the number past the 7 is a 3, so I'm not going to round up to 68. I'm going to leave it at 67. So that's about it for those. Once you figure out your pieces, you're just plugging those in. Here's the solution, which we just did, so we don't need to see that. Now, this is one for you to try. So copy this in your notes. Oh, well, you got the answer. Copy this in your notes. Try it. So try it and see if you get that for your answer. I will tell you that biannually means twice a year. So that is going to mean that your N is 2. All right, let's keep going. So example 9 is you invest $12,000 at an annual interest rate of 3%. Find the balance after 4 years if the interest is compounded quarterly. So that means I'm going to use the formula we just used. A equals P times 1 plus R over N to the NT. And then they want you to do it continuously. I'm going to use that other formula, which is often referred to as PERT. Because if you look at this, P-E-R-T, it spells PERT. So the E is going to be the E button on your calculator. So I'm going to do this in 2 parts here. So part A, initial amount is, this is example 9. So my initial amount is 12,000. My R is 0.03, so I already divided this by 100. My T is 4 years in both examples. And I'm compounding quarterly, so my N is 4. All right, so this is going to be, my final amount is going to be $12,000, 1 plus 0.03 R over N to the N times T, and they're both 4. So this is going to be 16, but if you put that in your calculator, when I put this in my calculator, I would probably change that to 16. So this is probably what I would punch into my calculator. And remember, put that in parentheses and then do another parentheses and then do 16. If you punch that in, you should get approximately 13,523.91. But practice punching this in your calculator. Make sure you get that. And that makes sense, right? 12,000, 13,500, that looks pretty good. You're going to see that compounding continuously is always better. So this means they're going to give you your interest 4 times a year. This means they're going to give you your interest the second you earn it. So this is your formula. I'm still finding my final amount. I'm still starting with my $12,000. So I'm going to have 12,000 times e to the 4 times 4 again. So that's going to be $12,000 e to the, oh no, this is wrong. Sorry. This is r times t. Sorry about that. 0.03 times 4. When you put that in the calculator, I would put it in like that. So the formula is r times t. R is 0.03. T is 4 years. So this is what I'm going to put in. So let's just make sure we know how to do this. So 12,000. And then I'm going to do my second natural log. And there's my e to the 0.03 times 4. And I get that. So I get 13,529.96222. And that is approximately $13,529.96. So you can see this is slightly better. The PERT answers are always going to be slightly higher than your compounding answers. Make sure your answers for all these problems have dollar signs rounded to 2 decimal places. That's what makes sense for money. If you're missing the dollar sign, you will miss some points. That's the answers, which we just did. Here's one for you to try. Again, 2 situations, quarterly and continuously. Continuously is where you use PERT, and quarterly is where you use the other one. So I would pause the video, try that, and then those should be the answers that you get. Okay, so those are all for exponential growth. You can also have exponential decay. So that's what's happening in this one. Now in this one, they give you the function. So this is a decay function. Notice that base is one of those measuring cup fractions. The a, remember we said that if a is between 0 and 1, then I'm decaying. You also know it's decay because I think it says decay in here. Well, up here it says radioactive decay. So pause the video, put this in your notes, and then we're answering 2 questions for this one. The first one says, what is the initial mass? So think initial is where you're starting. So that is when time equals 0. So here's my equation. 10 times 1/2 to the t over 29. If that was a little hard to see, it's a t over 29. And again, these are in your textbook, so you can always go to your textbook. So they're saying, hey, what is the mass when time is 0? So I'm just going to replace t with 0. So I'm going to get y equals 10 to the 1/2 0 over 29 instead of t over 29. Anything divided by 0 is 0, so this is 1/2 to the 0. Anything to the 0 power, that's 1/2 to the 0 power, so that's just going to be 10 times 1. So my initial mass is 10 grams. So that's all they're asking for there, initial mass. Now, if you think about it, in those other formulas that we used, this amount right here was always our initial amount or our starting amount when we were talking about money. It's the same for these decay. This is like a PERT equation, initial amount. We don't have a base E, we have a base 1/2. And this is a little different because it's a half-life, but this is our initial amount. And you can see when we plugged in time equals 0, we got that for an initial amount. Now in part B, they're asking how much of the initial mass is present after 80 years. So now T equals 80. So I'm going to do the same thing, but instead of T over 29, I'm going to have 80 over 29. And again, I can put that whole line in the calculator. Turn it on here. So I'm going to have parenthesis 10. I guess actually I don't need the parenthesis. I'm just going to do 10 parenthesis 1/2. Put that in parentheses, definitely. To the, put your exponent in parentheses because you're going to put a fraction in it. 80 divided by 29. Right, parenthesis, hit enter. Now these are decaying, so my answer should be something less than 10. And it is. It's 1.4777. I'm going to say approximately 1.48 grams. So these are pretty much plug in your given into the formula. Should not be too bad. Those are my solutions. For both of those, you could also graph the original function. So if I graph this function right here in my calculator, I'm going to get this. And then the questions that I'm answering is what happens when time is 0. So I can either look at my graph or I could go to my table and see what y is when x is 0. For this one, I could see what y is when x is 80. So you can see as the x values increase, the y values are decreasing because this is exponential decay. Okay, this is a different growth one. Instead of money, we're looking at population. I'll write this. Oh, here it is. I wrote it bigger already. So this is the function. This is kind of like a PERT because we got the E, but this number in front is always going to be your starting amount. And then here's your exponential growth portion in this example. So this is looking at fruit flies after T hours is given by this function. They say time is always positive, which makes sense. So it says find the initial number of fruit flies. So initial means T is 0. So when T equals 0, well, I already know if T is 0, they're asking for my initial amount. It's going to be 20. It's just like the one we just did, but we'll fill in the equation. So I'm finding Q of 0, which means I'm replacing T with 0. So I'm going to get 20 E to the 0.03 times 0. That's going to be 20 times e to the 0. Anything to the 0 is 1, so that's going to be 20 times 1, or 20. What are these? Flies. So they started out with 20 fruit flies. Part B, they say, what happens after 72 hours? So Q of 72 is going to be 20 e to the 0.03 times 72. So again, if you punch all that in your calculator, you're going to get approximately, I'm really going to round this to a whole number because these are flies, and I don't want to talk about partial flies. We only are talking about whole flies. So you should get approximately 173 for that. Again, you could graph this function in your calculator. So into y equals, you would put this, and then you would go to your table, or you could use your trace key, and you would find out what is y when x is 0, and what is y when x is 72. So 2 different ways to do these, algebraically or graphically. That is it for the second part of 3.1.